Okay, 5.4, solve trigonometric equations. Little note is already written for you. It says, until now we've been working with trigonometric functions and their graphs. Well, what if we wanted to find the value for specific points along the curve? In other words, the value for specific angles. So as a function, a sine function, moves along, it bounces up and down. The values repeat over and over again. Let's say it's a sine curve and we have our y-axis right here. Basically what we're asking is, can we determine the exact value at a certain point along the x-axis? Could we find the exact value of the here? Could we find the exact value of the function here? Could we find the exact value of the function here? Well, what if those x values aren't within one revolution of the unit circle? Then could we still find it? The answer is yes, and that's what we do today. So we're going to start by considering the trigonometric equation 2 times the sine of x minus 1 equals 0. The solution for this equation is all the values of x at which the graph of the function crosses the x-axis. So whenever 2 times the sine of x minus 1 equals 0, which is basically whenever it hits the x-axis, that's the solution for this equation. And we solve it basically applying the exact same skills that we would in other problems, such as a linear equation problem or a quadratic or another polynomial or a rational. We just start picking things away from x. So what we would do here is we would add 1 to both sides. We would divide both sides by 2. And then we can take the inverse sine of both sides. So now we have the sine of an angle is equal to 1/2. This is a ratio. So we would take the inverse sine of 1/2. That would get us x equals pi over 6. But there are two answers within the unit circle within one revolution. There are two solutions between 0 and 2 pi. And so we can use the values found on the unit circle in order to find that other solution that has the same sine ratio. So we go back to our unit circle and we see that the sine value for pi over 6 is the same as the sine value for 5 pi over 6. And so in this case, there are two solutions within one full revolution of that angle around the unit circle between 0 and 2 pi. What that basically means is that we can find, hypothetically, this picture does not match this work, but what we're saying is that if we find the value of the function at one place, it will have that value again somewhere else within one full revolution. Example 1, solve a quadratic trigonometric equation. So we're going to be applying our skills from grade 9, 10, 11, working with polynomials and solving and factoring and all of that good stuff, as well as the inclusion of trigonometric statements and functions, okay? So we need the exact solutions for the trig function 2 times the sine of x, sine squared of x, minus 1 equals 0. And we're just going to apply, and we're looking for solutions that fall between 0 and 2 pi.
That's the entire circle.
That's one full revolution. But remember, you could go around and around and around. You could have an angle of 4 pi or 6 pi or 2,000 pi, right? It just means you're spinning round and round and round and round that circle. So here we go. We're just going to solve this the way we would in grade 9. We're just going to add 1 to both sides. We're using BEDMAS in reverse here, right? Add 1 to both sides. Now divide both sides by 2. Now take the square root of both sides. Careful, on the left that's going to leave us with just the sine of x, but on the right the answer is plus or minus the square root of 1/2. And we can rewrite this square root of 1/2 because the square root of 1 is 1. So we can actually simplify to this statement, plus or minus 1 over radical 2. And that's more familiar because we see that on our unit circle. Okay, so now let's consider the two answers that we have. In case 1, we have the sine of x equals 1 over radical 2. In case 2, we want to deal with the sine of x equaling negative 1 over radical 2. Well, from your unit circle, you can go ahead and look at that if you don't have it in front of you. Otherwise, you can draw it. And the two places where the coordinates of sine are positive, 1 over radical 2, this is the sine, that occurs at pi over 4, a 45-degree angle, which means it also occurs out here at an angle of 3 pi over 4. So again, have your unit circle out, be looking for that. Sine corresponds to the y value.
I'm confused.
So one of the solutions where the ratio is 1 over radical 2
Sine's
is
the second number, right?
sine is y, yep. Corresponds to the y
That's
coordinate.
oh no, never mind. I was looking at 1 over 2. No.
Okay, so our two values is this occurs at an angle of pi over 4, so x equals pi over 4, and this occurs at an angle of 3 pi over 4, so x equals 3 pi over 4. So in the case where we're dealing with a quadratic, we've got two cases, and the first case has two solutions already. Well, another possible answer is that the sine ratio of x is negative 1 over radical 2. Well, where does that happen? Well, that simply happens down here. Okay, the coordinates of this point here are positive 1 over radical 2, negative 1 over radical 2, where the y coordinate corresponds with the sine ratio. So we'll look at what this angle is, going all the way around from our initial arm to our new terminal arm. This is x equals, and this is actually the second one that we could be writing, so I'll write it in the second spot. This is 7 pi over 4. And then it's going to have the exact same y value as this angle, which comes around. Basically, we need to take off 2 pi from, or sorry, pi over 2, which leaves us with 5 pi over 4. So the other angle that gives us a sine ratio of negative 1 over radical 2 is 5 pi over 4. Okay, so in our opening example, in the little note that we wrote down, you got two solutions out of a linear. Well, I shouldn't say linear, but like a 1 degree, or I guess it's still a linear trigonometric equation. Here we had a quadratic trigonometric equation, and we got 4 solutions. We should write a final statement. The solutions between 0 and 2 pi are x equals pi over 4, x equals 3 pi over 4, x equals 5 pi over 4, and x equals 7 pi over 4. If you were to end up using your calculator to get this answer, You could, right? You take the inverse sine of both sides, you get your calculator, it would push out a decimal, still measured in radians. But your calculator can only give you one of the answers. So from that, then you would need to use other information. You need to use properties of sine in order to get that second answer. Okay? You will run into that at times as well. All right, example 2. We have a quadratic trigonometric equation that we are going to solve by factoring. So here we go. We've got the square of the cos of x minus the cosine of x minus 2 equals 0. What you can do is you can simply, so I'm not going to use this strategy, but if it's helpful to you, you can say, pick a letter, let u be the cosine of x. And now you can rewrite that statement as u squared minus u minus 2 equals 0. And this is quite simple for us to factor. We know it's u plus 1, u minus 2 equals 0. So the solutions then would be u equals -1 and u equals +2. Then you could sub back, since u is the cosine of x, then you could say, okay, the cosine of x equals -1 and the cosine of x equals 2, and then you could go from there. That makes sense? It's essentially what we're doing. We're just factoring, but you can also just leave it in terms of this, and you can see that, I mean, you can still kind of picture it like this. At any rate, you're going to have two factors. First factor is going to be the cos of x plus 1. Second factor is the cos of x minus 2 equals 0, which tells us that we have the cos of x equals -1, or the cos of x equals 2. Okay? That is, that's just like solving our quadratics in any other case, except in this time we're not done. So we're going to deal with these two cases. We have case number 1, that's here, where the cosine of x equals -1. The only solution in the given domain, so when does the cosine of x equal -1? If you're looking at your unit circle, cosine corresponds to the x coordinate of any of those points on the unit circle. Well, it's a unit circle, so the x coordinate is only -1 once. And the angle is 180 degrees when that happens. So the angle is pi. Are you following that in your head? If not, I can draw it quickly. Basically, you have your unit circle. It has its intersections here at 1, 0, 0, 1, -1, 0, and 0, -1. So what we're looking at then is the place where the cosine of x, which corresponds to the x coordinate, is -1. Well, that's right here. That's the only place. So here's our initial arm, and here's our terminal arm, which means that we have an angle of pi. Okay, so the angle of pi, the cosine of pi is -1. So again, on your calculator, you could do this. You could take the inverse cos of both sides, but then it's going to give you a decimal. It's going to give you x equals 3.1415 dot, 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 dot. You don't want that, okay? You want it in terms of pi. So here, x equals pi. That is the only place within one revolution where you're going to get an x coordinate of -1, okay? Somewhat unique situation. Our case number 2 is where the cosine of x equals 2. Cosine corresponds to the x coordinate of any angle within the unit circle. Are we ever going to get an x-coordinate of 2 inside the unit circle? It's impossible. The hypotenuse is 1. So it can never, ever get to be a length of 2. Okay? So this case has no solutions. We can make a little note because the max value of cos x is 1. You don't need to draw this, but how else do we know that? Well, if you drew the cosine curve, cosine of x, which is what we're dealing with, its max value is 1. So it can't ever possibly reach a value of 2. No solution. Good. So then the only solution, if we combine our two cases, the only solution for this is x equals pi. So here we had a quadratic, trig, and there was only one solution, even though we got two cases. One of the cases only had one solution, and one of the cases didn't have any solutions. Okay? Well, if you think about it, that's the exact same as quadratic equations, right? A quadratic equation, you can come up with two solutions, one solution, or no solutions. Familiar?
Yep.
It's the same thing. Each case can have two solutions, one solution, or no solutions. Example 3, we have a slightly more difficult quadratic, and it is a secondary trig ratio. So there's another step involved. We'll write it down and we'll factor it. So we have 2 times the square of the cosecant of x plus the cosecant of x minus 1 equals 0. We're looking for the solutions that fall in the interval 0 to 2 pi, so 1 full revolution. And to factor this, I guess you just use sum and product. I'm just looking at how they did it, and I'm not seeing how they did it really.
Plus 1, and then cos x subtract 1.
Yeah, it's not difficult, but I'm just trying to figure out how we would do this in our heads. So again, I guess you could do sum and product, and you would have the product of a times c, which is -2, and you'd have a sum of the coefficient here, which is 1. So you're looking for two numbers that add to that add to 1 and multiply to -2. So those are +2 and -1. And then we use those to split the middle term. So if I'm looking at all of the steps, and you don't need to write this step if this is if you're beyond this. But if I split this middle term, I end up with plus 2 times the cosecant of x minus 1 times the cosecant of x minus 1 equals 0. And now to complete the factorization by grouping, from these first two terms I can pull out a factor of 2 times the cosecant of x. It leaves me with the cosecant of x, one factor of this squared factor, plus 1. Here I can factor out -1, leaving me with the cosecant of x plus 1. Now I have two terms. Each of them share the binomial factor. They both have a common factor here, a binomial factor of cosecant of x plus 1, so I can pull that out. And that factor needs to be multiplied by 2 times the cosecant of x, and it needs to be multiplied by -1. So this is an example where it might have been easier to say, okay, let's let u equal the cosecant of x and then go from there. But again, this is factoring by grouping. using trig functions within those factors.
I just factored it in one step.
Yep, that's fine.
It's infinitely easier to comprehend than that.
Well, this would be understanding it. At any rate, if you can go straight to here, that's fine and dandy. So that gives us our two cases. So now we have case number one. Case one is that the cosecant of x plus 1 equals 0, right? To solve one of these, for this statement to be true, one of these factors has to be 0. And our second case, case 2, is that 2 times the cosecant of x minus 1 equals 0. We can work these down. On the left, in the case number 1, the cosecant of x equals -1. And since the cosecant of x is equal to 1 over the sine of x, okay, we want to express this in terms of sine. So this is at the point where we would say, okay, let's get rid of our secondary trig ratios and make a little note over here. Cosecant of x equals 1 over the sine of x. In this case, it's really easy. If the cosecant of x is -1 over 1, what's the reciprocal of -1 over 1? It's just -1 over 1. So the reciprocal of -1 is -1. It's itself. Okay? So that also tells us then that the sine of x is -1. Well, we can get our exact solutions here. Again, if we look to our unit circle, sine corresponds to the y coordinate of all the points where the terminal arm would meet the arc. And the only place that occurs is down here, where we have 0, -1, which tells us that the angle that gives us a sine of -1 is 3 pi over 2. Okay, so the only solution here in case number 1 is x equals 3 pi over 2, or 1.5 pi. Now to case number 2. 2 times the cosecant of x equals 1. Add 1 to both sides. Divide both sides by 2. Now when we use this information and we take the inverse and express this in terms of sine, we get 2 over 1. Well, is there a value of x for which the sine of x is 2? Doesn't exist. No solution. Okay, so therefore the only solution for this equation is right here. In example 4, we have a somewhat real-world application. The range of an arrow shot from a particular bow can be modeled by the equation r equals 100, r equals 100 times the sine of 2 theta, where r is the range in meters. So range as in, here's the bow and arrow. Okay, here's the target. And this is what we want. Distance, in this case, is the range. Okay. We also have some other information. Theta is the angle above the horizontal. So here's our horizontal. It's the dotted line that goes straight across. And then, however we're shooting this arrow out, the angle that that makes with the horizontal is theta. So you can imagine that arrow is ideally going to go up and come back down and hit that target right on. If the angle is too high, maybe it goes too far. Or maybe if it's really too high, it comes down short. Okay? If the angle is too low, maybe it just goes down underneath it. So we're looking for the angle that's going to get this arrow to hit the target right on. Try to get my other lines out of the way.
So we want theta 2 equals, we want the function 2 equals 0 at,
Yeah. So you're right. We essentially have a
that's
sine curve. It's doing what a sine curve does. It hasn't been moved left to right at all. It's crossing through 0, 0 on its way up. And we want the range to be 80, is it meters?
Yeah.
Yes, 80 meters. Okay, so here we go. What are the restrictions on this angle? What are some things that theta can't be in this real world situation? What angles is it restricted to? Is it going to get shot this way? No. Is it going to get shot this way? No. Is it going to get shot this way? It could, technically. Okay, but you would probably say, no, it's going to go from 0 to 2 pi, and it can't get to 2 pi even because that's straight up, and what goes up must come down. Okay, so its restrictions is that x is going to belong to anything from 0 to pi over 2. I think I said 2 pi by accident, but this is pi over 2. So we're looking for solutions of 2 times theta that are then between 0 and pi. Let me explain that. So since theta cannot exceed pi over 2, 2 times theta must be between 0 and pi. I made a slight typo here just so we can follow it through. I called it x. We're actually dealing with theta. So theta, this angle of release, has to be between 0 and 2 pi, 0 and 90 degrees, which means in our equation, the angle that we're dealing with is 2 theta. It's going to be somewhere between 0 and 180. And hopefully that logic makes some sense. So that's our restriction, okay? Let's move on to solving. All right, we have 100 times the sine of 2 times theta, and the desired range is 80 meters. Suppose you could still be off left to right, but as long as you get the right trajectory, at least you got a chance. So from here, we just solve like we would any other problem. I'm going to keep this thing together, the sine of my double angle, and I'm going to divide both sides by 100. On the left, that's going to leave me with the sine of 2 theta. On the right, 80 hundredths is 8 tenths, so 0.8. Now, in order to get this sine away, in order to get 2 theta by itself, I'm going to take the inverse sine of both sides. That looks like this. This is going to tell us what this double angle is equal to, and then we can divide by 2 to get theta by itself. Turns out that 2 theta, so the sine of 0.8 in radian mode, is 0.927. That's an approximation, rounded. You could double check that in your calculator. Second function, sine 0.8, enter. Now we divide both sides by 2. Tells us that the angle that the arrow needs to be released at relative to the horizontal is 0.46 radians.
And then we multiply that by like 2 pi.
We're actually going to find a second possible solution here. Now this is the angle that it would be released at, but what we're finding out is that there are actually going to be two angles that it can be released at. So what we need to do in order to do that is we need to take this 2 pi, okay, which is right here. Maybe I'll just pull it off to the side. And the note is if 2 pi lands in quadrant 2, then, sorry if I keep saying pi, if 2 theta, if 2 times our angle theta lands in quadrant 2, then theta will be in what quadrant?
Quadrant 1.
It'll be in quadrant 1. Okay, so if we end up with, for 2 theta, angles that are over here, okay, then our answer theta will have angles over here. So any angle that falls within quadrant 2 or quadrant 1 for 2 times theta ends up being a solution for us that fits within our restricted range, restricted domain. Okay, so let's figure out what those are. We're going to use the trig identity. Use trig identity for sine. The sine of x equals the sine of pi minus x. So this is how you get the second angle, the second solution for the given sine ratio. Okay? So what are we working with? Our value of x is 2 pi right here. So we are working with pi minus 2 theta. We know that that equals pause. So, okay, if the sine, if 2 theta equals 0.927, and that's kind of like this guy right here, and then that means that pi minus x also equals 0.927. If the sine of x is the same as the sine of pi minus x, then x is the same as pi minus x. So if x is 2 times theta, then 2 times theta also equals pi minus 2 times theta. Okay, that comes from right here and right here. Since 2 pi theta is 0.927, pi minus 2 theta is also 0.927. Yay. So now we can subtract pi from both sides, or we can find out exactly what 2 theta is in this case. And we end up with 2 times theta is also equal approximately to 2.214. We can divide that by 2, and we end up with theta is approximately 1.11. So that is our other solution. And if this falls in quadrant 1, it's a good solution. We know it does fall in quadrant 1 because this falls in quadrant 2. Right? That's less than 3.14. That's less than pi. So this is a second solution for 2 theta, falls in quadrant 2. Therefore, once we cut it in half, our angle of trajectory here will fall within quadrant 1. So we end up with 2 solutions. They are 0.46 radians and
Can you lift the whiteboard a bit?
1.11 radians. And again, this second solution came from the trig identity, where the sine of x equals the sine of pi minus x, which means that x equals pi minus x. So we can take that from here. In this case, 2 theta is our x. and then we solve from there. So here you can do this basically pi minus something equals 0.927. That something is 2.214. Divide by 2 gets us our second angle. So what we figured out is that the archer can either shoot it at this angle of 0.46 or at this angle of 1.11. This will go 80 meters, and this one will go 80 meters. Make sense?
I see.
So in terms of the sine wave, it's exactly what we're saying. We're saying that if this is your distance, your range, and this is your angle of trajectory, then you can achieve the exact same range. Let's say 80 is somewhere up here. You can achieve the exact same range because we have an amplitude of 100. Okay, so it's going to reach 80. The max is 100. You can achieve the exact same range by shooting it at an angle of 0.46 and an angle of 1.11.